5, 4, 3. All right, so welcome to Channel 9. Can you introduce yourself and tell us where we are? What's going on here?
So we're on the 5th floor of the Smith Tower, which is Seattle's. It was Seattle's tallest skyscraper. In fact, I think the tallest skyscraper in West Mississippi when it was built in the first part of the 20th century.
Nice.
And so this 5th floor got renovated very beautifully for us by Microsoft.
Okay.
I'm Blaise Agüera-Yarcas, the architect of one of the architects in the Live Labs group, and I founded a company called Sea Dragon. We were acquired at the end of 2005.
Okay.
And we moved in here just a couple of weeks ago.
All right.
We started off in a loft in Ballard.
All right. So, very nice digs.
Yeah, it's really cool. It's sort
cool.
of, Matrix Victorian.
I noticed that. It's excellent. So, tell me about the technology that you're architecting.
Sure. So this is some of our dowry. So what we came to Microsoft with is the Sea Dragon technology.
Okay.
And this is really what caught the attention of Gary Flake, the founder of Live Labs, technical fellow. He started up Live Labs, and he really drove the acquisition of our company.
Okay.
And this is some of what it can do. So this is a collection of a few hundred photos. Okay, maybe we better not. Hang on.
That's fine.
Let's restart this one.
It's cool. That always happens. I mean,
only when you're demoing.
Of course. Only when you're demoing on camera.
Exactly.
Nice. Very cool.
Okay. So, collection of a few hundred images, and these are all kind of zoomable and pannable. These are a few megapixels each, but one of the beautiful things about this architecture is that there's our fearless acquirer, Gary. One of the cool things about this architecture, though, is that it allows you to interact with objects of arbitrary size. So this one is a map that's in the dozens or maybe even 100 megapixels. It's really high resolution.
Nice.
And it really makes no difference. One of the beautiful things about this model for interaction with objects is that you're only loading what you need at any given moment. So it's more like virtual Earth in that sense than like a classic kind of application model in which you decouple the opening of a document from navigation inside the document. You're doing both at the same time.
Interesting. So you're navigating on an image.
That's right. So in this case, I'm navigating on the image. Whatever I'm navigating to is what's getting loaded. If I'm zooming in, it's loading the high resolution content.
I see.
And as I zoom out, it's only loading the low resolution stuff. So that's why it doesn't matter how big an object is.
Interesting. So you must be using vectors. Are you using vector graphic algorithms, or
it's a combination? Actually, these guys are all raster imagery, although they're multi-resolution raster imagery.
Nice.
This is some of our team, as well as some newcomers out in front of our old loft in Ballard. That's before we moved. Here's an example of something that's a little bit more vectorish. This is all of Bleak House, the whole book.
Wow.
So here you can see this is definitely vectorish when we zoom in.
Certainly.
But when we zoom out, it's using a more pixel-based technique, and so we have these various kinds of approaches to combining vectors and raster and other kinds of representations for navigating through large collections. So this gives you a sense of some of what this Sea Dragon technology does.
Wow.
And it's very general. We have examples of this that are text, that are little applets, that are large images, that are maps. We have some very beautiful vector map demos.
Excellent.
So it's a raw technology that has lots and lots of applications. And so that was where we started. Now, a couple of months after the acquisition, I saw something really cool at TechFest. And it was a project that started off as a PhD project. So this was Noah Snavely's PhD project at University of Washington. He was co-advised by Rick Zalisky at MSR, and Steve Seitz at University of Washington.
Okay.
And it was just a fantastic project. The idea was that you take a collection of images of unstructured images taken in the same environment. So they took a bunch of images from, say, Notre Dame or the Trevi Fountain. They mined them from Flickr. So there were lots of cameras, lots of points of view, and they used some computer vision algorithms that were able to register all of those photos together into a common 3D environment. I might have a snippet of video that shows you something of how the algorithm works. Is that
Sure, that would be fantastic.
So let's find it.
Yeah, I think I remember seeing that at TechFest actually.
It was the most popular booth at TechFest, I think by a factor of 2. So it really captured a lot of people's imagination.
And for people who don't know, TechFest is our annual Microsoft research. Look what incredible stuff's going on, sort of internal event.
Alright. I think this will do it. So I'm filling out this one because maybe I can maximize it a bit better. So this is just a video of these guys doing a Flickr search and mining lots of pictures that are tagged Trevi Fountain. And so it's just a mixture of all different sorts of images. This is an example of one of them. And the algorithm works by finding a bunch of key point correspondences among those images and thinning those for consistency, and then it's able to reconstruct a three-dimensional model of whatever that common environment was that those images were taken in.
Wow.
Those pyramids are the camera positions. So it's not only figuring out what the three-dimensional environment was, but where the cameras were as well.
Wow.
And then they built this browser that lets you browse through those images in 3D.
Amazing.
So it's really cool stuff. And
so it's all based on just putting points in space around an object in an image, in a 2D image?
well, the way it works is that given an image, you can apply some filters to figure out which key points in that image are liable to be well conserved across multiple photos. So things like a corner of a window frame. Those are points in the image that if you photograph them from another point of view are likely to look pretty similar, even if the lighting conditions were different or the resolution was different. So it first identifies all those key points and describes them using a descriptor. And those descriptors in this case are these 128-dimensional vectors. And then
just 128-dimensional vectors, of course.
Well, it's a tricky problem. What you're trying to do is make a descriptor that's going to be invariant to things like the lighting conditions and the camera and so on, and also the point of view. But that's still going to be rich enough to describe a feature in a way that's distinct from some other feature in the same environment.
Wow.
So once you have those features and those descriptors, you're able to reconstruct the 3D environment by just saying, well, this feature in that image matches that feature in the other image, and here are the places on the image planes where those features occurred. If you now have, say, three features that match in two images, then that gives you really only a single way that those cameras could have been aimed in order to see those 3 points, and it tells you what the geometry of the 3 points is as well.
Certainly. Very interesting.
So that's basically the procedure.
Okay.
Now, when I saw this, I thought two things, and I think both of those thoughts have probably occurred to the MSR and UW teams as well, but maybe not quite in the same form. One thought was, boy, this would be a fantastic mix with our technology, because of course this really comes into its own when you do it in a distributed way, when you don't have to have all the hundreds of images all downloaded onto your hard drive, so you're just browsing the environment locally, but instead you're doing it in a client-server environment, just like the C drive technology. When all those images are out there somewhere on the web, brought together as a collection, and now I'm able to use a client and navigate through all of those remotely.
Interesting.
Otherwise, to browse an environment like the Trevi Fountain, you have to download a few hundred large JPEGs to your hard drive first. Right?
So now, just so that I'm clear, though, in the example of C-Dragon that you use, that technology. So basically, I'm going out, I grab a random image from the web, using your client technology. Regardless, let's say it's just a 65 kilobit image. I mean, it's not a super deep image.
Sure.
Not a lot of pixels.
Yes.
I can still interoperate with it like you are. So in other words, I can still navigate into it. You're going to do things to make it as nice as you can.
That's kind of an interesting question. So to really answer it completely would require that we go a little bit a little bit more deeply into the architecture.
Let's please do it.
You want to dive in?
Absolutely.
So, okay. The size of images on the web is right now constrained by the fact that you typically have to load the entire image before you can see it. Like there's a little bit of progressive image loading on the web, those two-pass things where you see first the blurry version and then the refined version.
Absolutely.
But it's pretty crude.
Okay.
And most images are not progressive. That's why images tend to be small. They tend to be 64K or something like that, 100K. You don't find 8 megapixel images on the web,
Sure.
even though that's what cameras take.
Yes.
So there are two reasons for that. One is that you have to download the whole damn thing. So if it's a large environment, if it's a high resolution image, then it'll take you a long time to load it, for the web page to load. The other reason is that the screen is too small, because web browsers are not tremendously scalable visually. You generally only look at things at their original resolutions. That means that a large image isn't of much use either. And if it's an 8 megapixel image and it's more than you can see on your screen at once, you won't be zooming in and out of that picture in your browser. So given those constraints, images tend to be small. When we browse large collections of images, like I was just showing, the way it works is that there's a collection object, which you could think of as being something like a web page full of thumbnails.
Okay.
So it has low resolution proxies for all those images. And that's why, even if the collection has thousands of objects, when you first load it, it loads more or less instantaneously. Because it's like loading the coarse resolutions of one picture that has tiny thumbnails of everything.
Got it.
And then those resolutions are progressive. One thing that you might have noticed in that Sea Dragon demo is that when you first zoom in on something, when something first comes up, it's a little bit blurry, and then it comes into focus gradually. We use all kinds of tricks to hide that process, but there's this kind of sharpening or focusing effect.
Okay.
So that works across entire collections with these collection objects. And then once you're looking at an object in more detail, if you dive into it or if you expand it, then it's going back to the original image and loading it at higher resolution. Now, if you have a 100 megapixel image, then you don't load the entire original image at once. You go to the original image and you load it progressively too. You load first the coarser resolutions and then the finer ones wherever you're looking. But the lucky thing about plain old web images is that they're so small anyway that having just one level of detail when you dive into one of those in a collection is okay.
Okay.
So that doesn't hurt much.
Excellent.
So we have technology that lets us scale up to images that are really big if they're stored in progressive and multi-resolution formats. Originally when we were a startup, we were using JPEG 2000. There are other alternatives that have similar kinds of properties as well. But if they're ordinary web images, then you don't need that multi-resolution for the final images. You still have that collection object that handles the multi-resolution for small scales, for coarse resolutions.
So forgive my ignorance here. I'm not a specialist in imagery. So an image file to me is just a bunch of bytes. It's just a bunch of random things. Not random, but they have meaning. So what you're saying is for these I can't remember the term you just used. Multi-resolution image. That's actually embedded in the information of the image itself.
Right. So it's a different way of sequencing the information. Okay. So if you have a file like a TIFF file, for example, the TIFF files are the size of the TIFF file is the size of the header plus the number of pixels times 3 bytes if it's RGB, for example.
Okay.
And it's just the pixels stored in reading order. You start at the top left and you store the first row of pixels and then the second row and then the third row and so on. So if I have a large TIFF file, like 100 megapixels, that'll end up being 300 megabytes, say, if it's RGB. And I stop loading it after the first 60K, then I'll have the first few lines, right? The first few lines of the file and nothing for the rest of the image. So that's in a way not a very effective way of ordering the information.
Sure.
What you'd like is if you load the first 64K, you'd like a fuzzy version of the entire image. And as you keep loading it, you want to holistically start refining it, start getting more resolution. Does that make sense?
So it does make sense.
Imagine that you just take the image and you downsize it by a factor of 2, say, and you downsize that one by a factor of 2, and downsize it again. You end up with what's called an image pyramid. And now you store the levels of the pyramid from coarse to fine, that is from low resolution to high resolution. That's a multi-resolution representation. And if you do that the right way, you actually end up with a file that's smaller than the original sequence of bytes because, because if you have large flat areas, for example, then the coarse resolution already contains all the information in a given region, and you don't have to waste very many bytes encoding the details there. So that's multi-resolution. The other thing we need is to be able to access a particular region at high resolution rather than just progressive in resolution, right? We need to be able to zoom in on one little piece of a 100 megapixel image.
Absolutely.
And see that part at high res without loading the entire thing at high res.
Wow.
So we need both multi-resolution and spatial random access. Does that make sense?
It does make sense. Now the question is, what's the construct that I'm actually viewing? Are you creating a new image?
Basically, yeah. The image that the client has in its memory isn't the same as the original image on the server side.
Okay.
It's a sparse version, meaning it might know what the image looks like in its entirety at a very coarse level, and it knows a little more about it at a finer resolution, close to where you're looking, and it knows a great deal about it at an extremely fine resolution where you're looking in the immediate vicinity of where you're looking. So it has a kind of cone of knowledge about that image.
Great.
It's sort of like a lot of these things are similar in some ways to the way the brain works with images. I mean, your sense of the amount of detail in the visual world is much greater than the actual amount of information that goes up the optic nerve. We have a fovea, which is a really high resolution part of the retina, and that's where we can read. That's where we can see really high detail. It's a very small region. We don't have the sense that the resolution of the world is a lot coarser outside the fovea, but it is. It's this kind of multi-resolution representation. We know about a very wide field of view at coarse resolution, and about a very small field of view at high resolution. And there's some intermediate ranges. This is sort of similar.
Absolutely. So, I mean, do you guys, architects in this world, do you study the eye and how that works? I mean, clearly you must. Well, you're trying to actually reproduce it to some degree.
Yeah, that's in fact, I'm not really sure how much it's really had to do with my work in this field, but my wife and I. Well, my wife is the serious one. She's a computational neuroscientist, and we actually met at a course on computational neuroscience. We both studied with a researcher, Bill Bialik, who specializes in at the time he was specializing in studying the fly retina and fly vision, and so she's done lots of done lots of serious work on vision in real animals. I've dabbled in it. Sure,
but it's no doubt helped you to some degree in developing your concepts.
Probably, yeah. I mean, it might be more like just I'm interested in that sort of problem, and
certainly.
And so I've been interested in it from the biological angle at various points, and also
very cool.
This other point of view.
So now, what are you working on now? I mean, now you're working for Microsoft, so yeah, I'm assuming you're not building this thing anymore.
Actually, we still are. There's a great deal that Microsoft can do with this technology. It applies in a broad variety of different areas. Some of which are probably pretty obvious from looking at the demo and thinking about it. But the one that's not so obvious is the mixture of Sea Dragon technology and this phototourism work from the UW and Microsoft Research. So we can go back to that. I can show you what we've done.
Certainly.
This is a tech preview that is going to be released in a little while. Right? We don't have a definite date yet, but the website and the video are going to be going live on Friday. So here's what that looks like. Let's this is just to prove that I'm still writing code, right? I'm launching it from my development environment.
Whoa.
So this is a collection of photos of St. Peter's Basilica in Rome. They were taken by Jonathan Doogie, one of our guys, on a trip to Italy a few weeks ago.
Okay.
And so we're transitioning among those images now, using that same technology. Here's what the 3D model looks like that was reconstructed from those images, and you can see that there are all these little cones and boxes. The boxes show what images, what these different images photographed, and the orange cones show where the photographer was standing at the time.
Wow.
So if we let's go back to this image, turn back on the cones, and you can see that there are some orange cones up here, which were this is when Jonathan went up to the top of the cupola and shot a bunch of pictures from up there. Let's take a look at what they look like.
Oh, that was really cool.
So this is him standing at the top, and you see I'm just transitioning from image to image, but it has this really sort of 3D look. It respects the geometry.
So how many images is that right there?
Well, here are all of them. So you can see that we're using a lot of that same Sea Dragon technology.
Yeah.
That's how these images are represented with that same multi-resolution approach. So this can now work over the network, over even a pretty narrow band connection.
Wow.
Same sort of experience. And they're all fused together in this three-dimensional environment.
That's fantastic.
Here are those cones again. So let's dive down to one of these pictures that he took in the middle.
Wow.
You see, we're just moving from side to side in the space, but we're doing it via images.
That is incredibly cool.
And these guys can also zoom in and out, and we can support very high resolution images and so on, just like we can in the Sea Dragon technology. It's based on the same stuff.
Sure.
Let's take a close up of that.
Wow.
So it's a really interesting way of navigating through.
I totally agree. It's an incredible way of navigating through pictures. I mean, basically, it's as though you're on the square, as opposed to looking at a series of pictures of someone that was on the square.
Exactly. Well, it's a mixture. I think the really cool thing about this approach is that it's, in a way, it's a slideshow, but it's a slideshow that is also immersive. So it's kind of halfway between a slideshow and a 3D game, or some kind of environment that's actually immersive in that space where the pictures were taken. So it certainly has interesting dimensions as an experience, but it also unifies those pictures and gives the sum of those pictures meaning and information beyond just the sum of the parts. What I'm trying to say is that the whole is greater than the sum of the parts here.
Absolutely, it's an emergent system.
There's something emergent here. That's right.
Certainly.
You've taken all those pictures that are in the same place, and by figuring out the geometry and where they were all taken, you now understand the relationships of all those photos to each other. Adjacent photos are hyperlinked in effect, and you know where all the cameras were. And if for example you tag one of those images, if I go and I tag the clock and I say this is the left clock, then all of the other pictures that also had the left clock in them would receive that tag too.
Wow.
So it gives you a way of knitting together all that information that has lots of implications for search and for other kinds of problems just having to do with analysis.
Absolutely.
Of content and images. So there's lots to this that goes beyond just the experience of flying through the photos in 3D. My other thought when I saw all this for the first time at TechFest was that beyond photo tourism, beyond just here are all the photos that I obsessively took of St. Peter's Basilica, because not very many people would really take hundreds of pictures of the Basilica from different points of view like that. It really gets interesting when you think about mixing together, about combining many people's photos and getting that emergent picture of the world based on all that photography.
Wow.
So if you think about taking taking the registration algorithms, the algorithms that fuse together those photos into coherent 3D environments, and putting them into, say, a web crawler that's going out there and indexing all the pictures on the web.
Yeah.
Then you start to get something pretty interesting.
Absolutely, and especially if those pictures are, tagged some way, such that it knows could be part of the system.
Exactly.
Because clearly, the algorithm that you mentioned earlier is actually figuring out on its own certain constructs and putting pictures together. Correct?
That's right.
It's not just somebody going, well, here's the one I took, at this angle and this angle and this angle. Now put them all together. They could be in random positions.
Oh, absolutely.
And it figures it out.
Exactly. The algorithm figures all that stuff out.
That's incredible.
It is. It is. And it means that. I mean, I've always been a little bit skeptical about tagging, per se, because it just seems like a very low leverage sort of thing to do. If I tag a particular rectangle in one of my images, it doesn't go beyond that image. It seems like a very work-intensive way of adding meaning to my photography. But if suddenly one person tagging one image somewhere with some details, if it's a picture of a fresco, and one person has taken the time to tag all the various saints on it and so on, if suddenly that means that those tags propagate to everybody else's photo that included that fresco, then that's a lot more interesting.
Totally, kind of like a global jigsaw puzzle.
Exactly.
With multiple people putting it together.
Exactly, it's something emergent that comes from just the photos and allows bits of meaning that come in through one end or another to propagate through the whole system. Even photos that aren't tagged have emergent meaning just from their context on the web. When we do an image search, the text on the web pages is being used to figure out what the meaning of the photos was. That's why if I type Notre Dame into A9 or something, I get a list of images.
Certainly.
Of that. Because of the textual tags that are just coming from the web pages.
Very cool.
So you think about all that cross-linking.
It's
you get
amazing.
a pretty interesting picture.
Oh, absolutely, interesting picture created by potentially thousands of different cameras.
Exactly.
Different experience, different angles, different. Very interesting. Now, for the developer perspective here, of course, the question is, how can I leverage this and use this in my application? Is there an API, is there a layer, is there some way for me to take advantage of the great work you've done and your team in doing the hardcore engineering and now saying, all right, you're presented with an API to play around and extend?
Well, we're a little behind with that part. So
that always comes last, obviously.
Well, hopefully not last. We're very, especially at Live Labs, we're really concerned with getting those kind of network effects. So we really want to open up some of these APIs and let mashups and development on top happen. So it's high on the list of priorities. We have at this point probably two different APIs that we'd like to be exposing eventually. One to the Snapdragon architecture in general, and another specifically to the kind of linking and georegistration that would be enabled by this photosynth stuff. So I can't tell you anything definite about when we when that's going to happen, but it's.
But you're thinking about it. You're the architect, so that's good news.
It's certainly in the pipe. It's a very high priority for us.
Very cool. Now, back onto the architecture of the product. You're not using the .NET 3.0 technologies, are you?
No. When we were acquired, we were using OpenGL 1.1 and C++. And we're now using DirectX and C++.
Okay.
And we're still using DirectX. In fact, I think we may still be using DirectX 8. We wanted to really build this on as widespread a platform as possible. We didn't want to impose barriers to entry.
Certainly.
So, in theory, this stuff could probably run on a Windows 2000 box.
Nice.
Though maybe I shouldn't be quoted on that. Yeah. Certainly, any XP box will be able to run this.
Very cool. And it would be possible to build, probably with a fair amount of work, a managed programming layer on top of this.
Yeah, that's right.
Exactly what Avalon is doing. They're writing their layer on top of DirectX.
Exactly.
Right. You don't have to go right into DirectX. You don't have to be an architect with a PhD as yourself to be able to do things like this.
Well, actually, I never quite finished my PhD.
Well, you sound like it. Certainly you're building great stuff. But I mean, the point is you're an expert at that DirectX programming level, which does require...
I don't know so much DirectX either.
Oh, no. Man, that's strike two. Let me see if I get this one right.
Well, no, but you're
you see
right.
what I'm saying?
Yeah, you're right.
Yeah.
It's,
DirectX is hard to program against in native code. It just is.
a lot harder than OpenGL is, as we've found out in the past few weeks.
Okay.
Yeah, the hope is that we have this engine underneath that's built using simple moving parts that are very common and I guess in some ways legacy. They're not. It's not modern. It's not using the common language runtime or anything like this. And we hope to make it easy to hook up that engine, which was really designed for wide compatibility and high performance.
Okay.
So there's nothing managed in there at all.
So that would
make it easy to hook that up to higher order constructs, more modern things.
Sure, which clearly is where our platform, the future is going for programming, it seems. But managed C++ is pretty amazing as well. The latest version of C++ is pretty impressive. I've done a few interviews on that, but that's orthogonal. So,
yeah, I think it's synergistic. I mean, when you're concerned with coding, and I know that this is also in very rapid motion. This whole field is developing very quickly now. But my sense is that it's still going to be a little while before, say, high-performance game developers switch from using straight unmanaged C++ to writing high-performance games in managed code. There's still just a little bit more performance to be eked out, a little bit more generality, a little bit closer to the machine. And this is a little bit like a game in that sense. We're really operating pretty close to the hardware. The difference is that a game is generally a closed system, although Xbox Live may be changing some of that. But it's a fairly closed system, and here we want to make it an open system. So we want to create those APIs, those sockets that let managed code, that higher order stuff connect.
Very cool. Now, so you're programming against the GPU.
Yes.
Right. So, how do you handle? So you mentioned that one of the interesting scenarios was the notion of distribution, which clearly was I'm going to want to have. Anybody's going to want to have in a web environment, right? So I do a search and I want to be able to grab all these images in parallel. So, are you guys doing a lot of work with asynchronous web request type stuff?
Yes.
Okay.
In fact, the current generation of photosynth, our builds as of last week, we're working exactly with those kinds of asynchronous web requests. Okay. That is the backend that we're working against.
Very good. Cool. Yeah, I just did an interview with the coordination concurrency runtime people. They've developed an excellent model for writing several, parallel processes happening obviously in parallel, but in a much easier way than dealing with the threads directly. They've abstracted things away nicely, and they're using the notion of coordination of ports and stuff like that. It's very cool stuff. But you only get it in managed code.
Yeah, that's
you only get it in managed code because they rely on generics. You could say, well, you got templates in C++, but they rely on 2.0 of the framework to do what they do.
Well, from what I've seen, there are a lot of really interesting tools that I've sometimes wished that we had easier access to that are now being done for managed code APIs. It looks great. This stuff looks great. So who knows? We may be doing a managed code rewrite in a couple of years. I hope we don't have to.
You probably don't have to. No way. But that looks really great. So, we don't know when this is coming out exactly, which is fine. We don't know
exactly. That's right. As I said, the video and the website are going live on Friday.
This Friday.
Okay. Very soon. And I think it's safe to say that we'll have a tech preview in the fall with a bunch of canned collections.
Cool. I'll try to get this video out on Friday then.
Excellent.
That would be good. Well, anything else you want to tell us about this technology?
I don't know. It's too open-ended a question.
You're an architect. You live with open-ended questions.
Fair enough. I've probably gone about to the limits of what we really should be talking about at this point.
Fantastic.
But it's my feeling that this approach to images really has the potential to change the way not only the way we interact with our own pictures and the pictures on the web, but the way we think about the web itself. Pictures are ubiquitous on web pages.
Absolutely.
The pictures on web pages are connected to the content. If you think now about relating geometrically and geographically all of the pictures on web pages with each other, that forms links and connections between the web pages that, with a little imagination, you can think about how that might really change your experience.
Absolutely.
How you browse the web. Using those photos as portals and web pages and so on.
Wow. I mean, it's like taking this, remember the vermal thing?
Yeah, exactly.
Taking that to a whole new dimension.
It is.
Right? I mean, clearly, several dimensions.
Well, and it's an interesting comparison. I think that one of the big problems, well, there are a lot of problems with vermal, of course, but one of the worst things about it was the authoring story. It's not very compelling when, in order to make something like that happen, a 3D experience happen, you have to go through an exercise in CAD. That guarantees you that not very many environments are going to get made. So it's a little bit like what Yahoo started off as being. The idea was there was going to be a directory of the whole web. It was like the encyclopedia of Diderot and Alembert, this attempt to try and catalog all of human understanding from the top down. And one of the lessons, I think, of Web 2.0 and the kind of thinking around that is that you really should be trying to leverage what's already there and put it together in interesting ways that come out of the content itself.
Absolutely.
That was really what I think what Google's big insight was in their search engine, and so this is like a step in that direction for images.
Absolutely. Well, I'm really looking forward to seeing this when it comes out. And do you have? Does your team have a blog or? Blog age now, so way for customers.
You cannot have a blog, right?
Yeah.
So we're going to have one on the Photosynth site.
Okay.
I'm not sure if anybody has actually put any interest in it yet. We've been pretty heads down to try and get our first release on. But
when I put this on Channel 9, you'll become a Niner, right? Maybe spend a little time answering some questions if you have the time.
Sure.
And
I always have the time. Yeah, we'll be blogging.
Excellent. Very cool. Well, hey, thank you for your time and nice to meet you.
Thanks so much. You too.
You're architecting.
Sure. So this is some of our dowry. So what we came to Microsoft with is the Sea Dragon technology.
Okay.
And this is really what caught the attention of Gary Flake, the founder of Live Labs, technical fellow. He started up Live Labs and he really drove the acquisition of our company.
Okay.
And this is some of what it can do. So this is a collection of a few hundred photos. Okay, maybe we better not. Hang on.
That's fine.
Let's restart this one.
It's cool. That always happens. I mean,
only when you're demoing.
Of course. Only when you're demoing on camera.
Exactly.
Nice. Very cool.
Okay. So, collection of a few hundred images, and these are all kind of zoomable and pannable. These are a few megapixels each, but one of the beautiful things about this architecture is that there's our fearless acquirer, Gary. One of the cool things about this architecture, though, is that it allows you to interact with objects of arbitrary size. So this one is a map that's in the dozens or maybe even 100 megapixels. It's really high resolution.
Nice.
And it really makes no difference. One of the beautiful things about this model for interaction with objects is that you're only loading what you need at any given moment. So it's more like virtual Earth in that sense than like a classic kind of application model in which you decouple the opening of a document from navigation inside the document. You're doing both at the same time.
Interesting. So you're navigating on an image.
That's right. So in this case, I'm navigating the image. Whatever I'm navigating to is what's getting loaded. If I'm zooming in, it's loading the high resolution content.
I see.
And as I zoom out, it's all loaded.
5, 4, 3. All right. So welcome to Channel 9. Can you introduce yourself and tell us where we are? What's going on here?
So we're on the 5th floor of the Smith Tower, which is Seattle's. It was Seattle's tallest skyscraper. In fact, I think the tallest skyscraper in West Mississippi when it was built in the first part of the 20th century.
Nice.
And so this 5th floor got renovated very beautifully for us by Microsoft.
Okay.
I'm Blaise Agueda-Yarcas, the architect of one of the architects in the Live Labs group, and I founded a company called Sea Dragon. We were acquired at the end of 2005.
Okay.
And we moved in here just a couple of weeks ago.
All right.
We started off in a loft in Ballard.
All right. Very nice digs.
Yeah, it's really cool. It's sort of, Matrix, Victorian.
I noticed that. It's excellent. So, tell me about the technology that you...
The Sea Dragon technology does.
Wow.
And it's very general. We have examples of this that are text, that are little applets, that are large images, that are maps. We have some very beautiful vector map demos.
Excellent.
So it's a raw technology that has lots and lots of applications.
Mm-hmm.
And so that was where we started. Now, a couple of months after the acquisition, I saw something really cool at TechFest. And it was a project that started off as a PhD project. So this was Noah Snavely's PhD project at University of Washington. He was co-advised by Rick Zalisky at MSR, and Steve Seitz at University of Washington.
Okay.
And it was just a fantastic project. The idea was that you take a collection of images, of unstructured images taken in the same environment. So they have low resolution stuff. So that's why it doesn't matter. It doesn't matter how big an object is.
Interesting. So you must be using vectors. Using vector graphic algorithms, or
it's a combination. Actually, these guys are all raster imagery, although they're multi-resolution raster imagery.
Nice.
This is some of our team, as well as some newcomers out in front of our old loft in Ballard. That's before we moved. Here's an example of something that's a little bit more vectorish. This is all of Bleak House, the whole book.
Wow.
So here you can see this is definitely vectorish when we zoom in.
Certainly.
But when we zoom out, it's using a more pixel-based technique, and so we have these various kinds of approaches to combining vectors and raster and other kinds of representations for navigating through large collections. So this gives you a sense of some of what